Hi, welcome back to MEEN 221 Statics and Dynamics. Today we are going to talk about some worked examples. As with worked examples, what I want you to do is couple of things. First, before we start the worked example, I want you to go get a pen, notebook, calculator. Okay, because I want you to work these examples with me so that you will understand how this thing goes. Okay, so that's the best way to learn, and as I've told you many times, you cannot build muscles by watching an exercise video. You have to actually do this. Okay, so let's start. So we are first going to talk about a very simple problem. In this particular case, we have a cable system which is carrying some heavy load. So this is supposed to be a crane, and the crane is carrying some load here. And we want to find out whether it is safe, because people are going to move around. This kind of thing you can see fairly commonly in a dock or some place like that. Usually what it says is, notice, can you see this 45-degree line? So you cannot typically you cannot put a rope that's below 45 degrees. Now let's see what it says. It says that each rope is capable of supporting 130 pounds. And it makes an angle of 30 degrees from the vertical. So that's okay. And we are going to look at whether a 1/4 inch eye bolt, that is this thing, is safe enough. That's what we are trying to find out. So notice how we are talking about structural safety here. Okay. So in order to do this, we have to do two things. A, find out how much load an eye bolt can take. B, this is usually called the supply. Okay, and B, how much do we need? And this is usually called the demand or the load demand. And if demand exceeds supply, you know you're in bad shape, right? So that's how it works. So where do we find this information? This is usually found in the manufacturer websites for eye bolts. So you're wondering, manufacturing websites have a wealth of information, and that's one of the things you have to learn, how to utilize manufacturing websites in order to get data. Why do the manufacturers put in all these data about how to use their products? Because they don't want you to call them, and ask them how to do it, because that's expensive. What they will try to do is give you as much information as you can so that you can build it yourself, and in a way that is safe for them. Okay, so let's look at what the manufacturer says for what is allowed for eye bolts. So here it is. Look at this thing, and first thing I want you to notice is, look at this, lots of information about eye bolts, because eye bolts are one of these critical things. So first thing we look at is eye bolt lifting capacities. So if you want, you can pause here and stare at it for a few minutes before you continue. I'm just going to continue. Okay. So what it says is that we are looking at a 1/4 inch eye bolt. That's here. That 1/4 inch eye bolt, right? And you run your fingers along this and you say, okay, at 0 degrees it can take 500 pounds. At 45 degrees it can take 125 pounds. And over 45 degrees it says, no, don't use. That's very clear, very simple. Okay, but that's not the only information that's there on eye bolts. If you look here, if you look around here, which is the other place I want to kind of show you, it will have a lot of information about what are the different pieces of information. It tells you how was the eye bolt cast, what is the cavity number, what is the shank size, what is the forging code, which tells you which piece of equipment was used, what is the heat code, what is the, there's some logo, all kinds of things. Okay, so first thing I want you to realize is that people want to make sure, because eye bolts are very critical for load carrying, and since they are in dangerous situations, people want to make sure that they can track any errors in an eye bolt. That's why they have all this information. So we have 1/4 inch eye bolt, we have 500 pounds at 0 degrees, 125 pounds at 45 degrees. Okay, so now let's go back to our problem and take a look. So what I'm going to do is I'm going to draw one of them. So I'm going to draw, here is the eye bolt, right? Here is the 45 degree line. That's one of the nice things about having a graph paper background, because you can draw all these things. Here is the x-axis, here is the y-axis, vertical axis, and the cable is like that, and it makes an angle of 30 degrees here. So this angle is 45 degrees, and so this angle is 15 degrees, and F is 130 pounds. This is the safety line, and the supply says 125 pounds at 45 degrees and 500 pounds at 90 degrees, or sorry, at 0 degrees. So that's pretty good. So it's clearly the load is less than 500 pounds. So we will be perfectly fine. But on the other side, notice that yes, the supply is 125 pounds at 45 degrees, but the angle is 15 degrees away. So we have to say, is it still safe, by projecting and asking, is this more than 125 or not? How do I find that? Well, we know projection equals magnitude times cosine of the angle. Okay, so this is our trigonometric way of doing it, or the geometrical way. So in our case, that is 130 times cos 15 degrees, which turns out to be 126 pounds. Okay, it's clearly more than 125. So you would conclude that the magnitude is this, angle is 15 degrees. That's that. So it tells you not quite safe. So what should I do? What I would do is I would go back, look at the manufacturer's site and say, what is the next thing that I can recommend? So you can go back up here, blow it up, and you say, hey, wait a minute, I can do the 5/16. Can you see the 5/16, which is called a M7 in the metric system? The 5/16 can take 225 pounds at 45 degrees. The supply is quite a lot. So if I graduated from the 1/4 to 5/16, I will be quite safe. So I would say this. Recommend use 5/16 or higher. Why do I say higher? Because many times you don't want to necessarily go for the next higher one. You may want to go for something that's in your warehouse, right? So there's a question of, do you really want to run out to the store and buy a 5/16, or can you do something that's bigger? So there might be other considerations that go, but you know that for safety's sake, it has to be at least 5/16 or higher. But I want you to point out the entire story. So this was the supply, this was the demand. So demand comes from calculation. So I'm going to write this down. Demand is what we calculate. Supply is based on what the manufacturer okay, and notice that based on our calculation, this is our decision. Notice how calculations aid our decision. So before we go, there are two items that I want to mention. The first one is the following. Supply minus demand is called safety margin. supply divided by demand is called safety factor. So when you look at an engineering manual or something like that and it says safety factor, it always means supply over demand, and safety margin means supply minus demand. Okay. So as far as this problem goes, we are done. But I want to show you how to do the same thing out of vectors. Why do we do that? Because you should always have more than one way of doing things. And second thing is I'll show you how a systematic vector approach would just work. Here you needed to know something about how to make sure what angles to use and all of that. Vectors are a little bit easier on that front, but the price you pay is more calculation. So let's see how to do this with vectors. Vector approach. So how do we do this? Okay, our same problem is here. Here is the force, 130 pounds. This is the angle, 30 degrees. This is the x-axis. This is the 45-degree direction. And this angle is 60 degrees. So we want to say demand equals component of force of F in the 45-degree direction. So first we have to figure out what do we mean by direction. Direction in vector speak, this is unit vector, magnitude 1 at angle 45. So I'm going to write E equals 1 cos 45 degrees, comma 1 sin 45 degrees, which turns out to be 0.707, comma 0.707. Okay, that's direction. So I now have the direction. Now what about F? F is 130 pounds, that is magnitude, at what direction? So notice 60 degrees from positive x-axis. So 60 degrees CCW. So I'm going to write it CCW from positive x-axis. Because I want to remind you for a few times so that you know how to calculate this. This turns out to be 130 cos 60 degrees, comma 130 sin 60 degrees, which turns out to be 65, comma about 112.6 pounds. Okay. Now component equals dot product with direction. That's what component means. So we know how to do that. F dotted with E will turn out to be 65 times 0.707 plus 112.6 times 0.707, which turns out to be 126 pounds approximately. Okay, so both ways give you the same answer. Notice this is more systematic and it has one other advantage. This can be extended to 3D. Which is where we are headed with the next example. Okay, thank you very much.